All right. The second tutorial is on coefficient functions. Okay. Is everybody ready for the second tutorial, or if there is some urgent issue that we need to resolve, then should I just proceed with the second? Okay. All right. So while personalized help is available to everybody who has issues, I'll proceed along introducing the concept of coefficient functions. Okay. Coefficient functions are representation of functions in NGSolve. So a function is a function of variables x, y, and z usually, and x, y, and z are themselves functions on a mesh in NGSolve. So you can do many things with coefficient functions. So this tutorial will try to cover as much of that as possible. So you see here we have about 1, 2, 3, 4, 5, 6, 7, 8, 9, about 10 things that we could do with coefficient functions, and there's more, but so that would give us about 1 minute to discuss each of these. But let's make sure that you pose a question when something is not clear. Okay, so coefficient functions. Let's do the same import commands that we did before. We imported the GUI, we imported the unit square again, and then imported everything from NGSolve, and we created a simple mesh. Okay. Now, once you have a mesh, you go back into the cell, into the Jupyter cell, and execute a command like this. My function is x times 1 minus x. That's a function. Okay. So you can do things with this function, including visualizing it. We'll visualize it in a second. But the first thing to note is that this x, how does it know what this x is? Well, x was already imported into the workspace when you said from NGSolve import everything. So if you had an x in your previous workspace and x was something else, that x is gone, and now you have the NGSolve x. And NGSolve's x is itself a coefficient function. Okay. And similarly, you have coefficient function y and z in 3 dimensions. So if you want to visualize the function that we just created, well, here is the command. Draw my function mesh, and you give it a name. Okay. This is whatever name you like to give it. Okay. You see the coefficient function in the window. Okay. You can ask for the function to be evaluated at a certain point and return a value. Okay, so for example, at the point x equals 0.2, y equals 0.2, you ask the value of the function, and you can verify that this is the correct value. Okay, so one thing to note is that you can't just say my function parenthesis 0.20. You first have to create a point, and Mesh knows how to create a point. It's called a mapped integration point in NGSolve. You create a point, and using that point object, you evaluate the coefficient function. Okay, if you can evaluate the coefficient function at one point, of course you can evaluate it at a collection of points. So for example, if you have a complex solution and you want to evaluate it across a line, then here's an example. Here are xy coordinates of a line where the y coordinate is constant and the x coordinate changes. You can evaluate it at all of these points. You may plot the value of the function along that line. And for that, you can use Python's facilities with matplotlib. And you see that along that line, the function looks like this. Okay, now a little bit about the internals of coefficient functions. Coefficient functions are stored as expression trees. So you can print the expression tree by simply printing the function. Okay, if you print the function, you get this output. So let's go over this output and parse it slowly. So this function was x times 1 minus x. So it's a product of x and 1 minus x. So if you look at the output, you see the product coming up first in the expression tree. And then the leaves of the tree are the two branches of the product, right? You're taking two things and multiplying them together. So you have a product here, a coefficient function x here, and the 1 minus x is again represented by all of this. So 1 minus x itself is a tree with minus at its head, and the operation being performed, this binary operation being performed using minus is 1 minus x. Okay. All right, you can integrate a function on the whole domain using your mesh. What this will do is you runs a loop over the elements and integrate on each element using a quadrature rule appropriate for the element. And you can change the quadrature rule as you like by providing more keyword arguments to this function. If you type help integrate, then you get all the possible options that you can do. You can differentiate a coefficient function. Last year you could not do that, but this year you can. The new function that is added is diff, and this is a symbolic differentiation. Okay, so here's our simple example of a function x times 1 minus x. You differentiate with respect to x, and you can ask to plot that computed derivative. And if you really would like to know what's going on behind the scenes, and you think of differentiating x times 1 minus x, and you have to apply the product rule. So this automatic differentiation implements the product rule, and if you parse this tree, spend some time looking at it, you will see that this is an implementation of this product rule. Okay, I leave you to look at it if you like, and while I proceed to the next topic in the coefficient function, which is parameters. Okay. Often coefficient functions have parameters. Parameters are constants whose values you want to change later as a solution or as the computations proceed. So here is the keyword parameter that defines some quantity to be a parameter. You have to give it an initial value, but it knows this as some kind of a symbolic quantity whose value might be changed later. Okay, so here's an example of a low frequency sine wave. Low frequency because k is 1. Now you may decide to change the f by changing the frequency value k to 10 instead of 1. And then you see that the coefficient function's definition need not be changed. It's the same coefficient function becomes different with a different value of k, with the new value of k. It's also instructive to look at the expression tree for a coefficient function which has a parameter, and you see the expression tree for this sine of k times y. It has sine at the top of the node as a node in the tree, and then there is a multiplication of k and y, and you see that k is actually a node in the tree. Right? Okay. So and whenever you have an expression tree like this and you have a node in the tree, you are able to differentiate with respect to that node. So therefore, this coefficient function can be differentiated not only with respect to x, but also with respect to k. So here's how you differentiate with respect to k. Instead of x, you just plug in k. And you can differentiate sine of k times y in your head, and you find that the derivative must be this, and you can verify that it has done the derivative correctly by say, integrating the difference. Okay, the next topic is interpolating a coefficient function. As you saw, coefficient functions are written out as expressions in x and y. They're not really finite element functions. You can take a coefficient function and bring it into the finite element space. For that, you need interpolation. So here's how you interpolate. There's a command called set. Okay. So declare a finite element space, in this case, the Lagrange finite element space that we saw in the very first tutorial. Declare a grid function, an object which has memory to allocate vectors, and then ask the grid function to interpolate my function. All right. Okay, so you might ask, okay, what is happening in the background? Well, set does an interpolation. It's a general purpose interpolation meant for all finite element spaces in NGSolve. So it has to be general enough to handle all finite element spaces. So it does something a little complicated called the Oswald interpolation. First, it zeroes the function, then it projects the function, the coefficient function, on each element in L2, and then depending on the finite element space's conformity requirements, it averages the degrees of freedom that needs to match across the element interfaces. So that's now there is a more canonical way to do finite element interpolation for each finite element using its own degrees of freedom and so forth. And Joachim will speak about this in 2.10, which would be in the afternoon. All right, so we go back to the function. The coefficient function did not have these wiggles. When we interpolated, we got some little wiggles here because the interpolation is not an exact process. Okay. There is no requirement that the coefficient functions be scalar functions. You can have vector functions. The only thing you need to know is vector functions need to be put inside a tuple. If you have 3 components in 3D, you need to put it in a tuple. If you have 2 components like here is the first component, here is the second component. Right? And you can draw vector functions as well. But you have to go here in the visual menu, and then you have to turn on draw surface vectors to actually see the vectors. So without clicking this, you don't see the vectors. Right? Now you see the vector field. And if you just want to see the vector field without the underlying scalar field, you take the scalar field and say, don't show me any scalar field, just show me the vector field. Okay? And if you want a finer spacing in which you want to plot these arrows, you move this grid. Okay. All right. You can take a scalar function and plot it and ask for its gradient, and that becomes a vector-valued coefficient function which you can plot. Here is how you take the gradient, just using grad. Okay. All right. So now we come to some features that were not explained previously in previous years, but it's gotten to a point where things have matured that we can provide this documentation on compiling coefficient function. Okay, so here's our same old coefficient function, x times 1 minus x. Okay, and we ask it to compile. Okay, what happens? Well, originally the function had an expression tree that looks like this. After you compile, the expression tree has become a sequence of linear steps. It's not a tree anymore. It's a program, and the program has 3 steps, and once you do all these 3 steps, you've evaluated the function. The advantage of this over this is that in a tree you might have many repeated nodes. So if you traverse the tree, you're computing the same quantity over and over again. Whereas here you compute one quantity, you have that result in as an output of one of the steps, and so you have a lot of optimization that you can do. Okay, so to read this is you have to read this as if it were a program. You say, okay, step 0, you take the value of the coordinate function x. Step 1, the value 1. Step 2, the binary operation that takes as input the outputs of step 1 and step 0. So I've tried to explain it here. In step 2, we're taking the output of step 1, which is 1, the output of step 0, which is x. So the output of step 2 would be 1 minus x. Okay, so once you know how to read this, this would make sense. Okay, you can construct more complicated functions, compile it, and then spend all your day looking at these printout of expression trees. Okay, to illustrate the point, here is another example, perhaps a contrived example. You start with a simple function, multiply with y, multiply with itself, and do lots of things, and you can see that there are lots of intermediate quantities which if you don't if you have to recompute all those intermediate quantities, then you're spending a lot of time repeating the computations instead of saving the results of the computation. So we can try to see what's the difference between a compiled coefficient function and a non-compiled coefficient function. Here is the non-compiled coefficient function defined here, and the same function has been compiled here. So we look at how much time it takes to integrate without compilation. That's to integrate on this mesh that you see on the side, it's about 663 microseconds. Whereas if you compile, it's about 10 times less, 68 microseconds. Okay, now for those of you who have NGSolve built from source, there is one further option. Because if you build from source, then the assumption is you have a compiler. And that compiler then creates the NGSolve creates a wrapper around that compiler, and you have an NGSolve compiler. And using that, you can compile even further in the sense that you can bring all the optimizations that the compiler can do, but beyond NGSolve, all of that can be brought into the coefficient function. And for that, you have to do this. Okay. Well, okay. So at this point, it has generated some C code, and if you look at the folder where you're running, you'll see some automatically generated C++ files floating around. Those are the C++ files corresponding to this particular coefficient function. And if you integrate using the real compiled coefficient function, you get a further reduction in time. Okay, you can print out these coefficient functions. It's going to get, there's a lot of steps. This is not wanting to explain this. But okay, the point is, if you look at the one that is not compiled, you see a tree that goes on pages and pages and pages and pages and pages. Okay, well, you sort of get the idea. So, okay, so that concludes the discussion of coefficient functions.